MIT time for the defense. Oh, there's Victor.
Do you know Dan?
Dan who? Oh, Daniel?
Yeah.
Yes, Amy and Daniel are my friends.
All right, I think we have a quorum. So why don't we get started? Welcome everybody to the Thesis Defense for Mandy Korpusik. My name is Jim Glass. I'm Mandy's advisor, and her committee members are Peter Solovitz and Victor Zhu. Just a reminder that the Thesis Defense has two parts. The first part is open. Mandy will make her presentation. We'll have some Q&A at the end, and then afterwards we'll ask everyone to please leave the room, and hopefully we'll turn off the live streaming, and the committee will meet privately with Mandy, hopefully. You never know these days. Before Mandy gets started, I just want to say a couple of words. She came to MIT in the fall of 2013, I think, from doing her undergrad at Olin College. And she got involved in a nutrition project that Stephanie Seneff and I were just getting underway in collaboration with some nutritionists at Tufts University, Susan Roberts and some of her colleagues. And it was a real-world application, helping people talk naturally about what they were eating, people who wanted to log. And so it was a good application of speech understanding technology. It was also an era where the state-of-the-art techniques like conditional random fields were being overturned, I guess, by the wave of deep learning. So Mandy came in this era, and through the years has explored a number of different interesting applications of deep learning models to spoken language understanding that she'll talk about in her thesis, and has produced many publications, I think 8, maybe 9, hopefully, depending on how the latest reviews go. And so it's been quite productive in this area. And I think with that, I'll leave it over to Mandy.
Thank you, Jim. Good morning, everyone. My name is Mandy Korpusik, and I'm excited to be here sharing with all of you my PhD thesis defense. So today I'll tell you about my work on deep learning models for spoken dialogue systems with a specific application to the nutrition domain. The motivation for our work on diet tracking stems from the rising obesity rate in the United States. So in the 1960s, only 13% of American adults were obese, and that rose to 40% in 2016, and led to an estimated medical cost of $147 billion in 2008, according to the CDC. And at the same time, today, many Americans care about tracking their diet for a variety of reasons. Maybe they are obese and care about weight loss, or they might be interested in fitness and health or bodybuilding. And also people are following popular diets like eating gluten-free or vegan or keto. So people on these diets need to really understand what nutrients they should eat in order to maintain a healthy, balanced diet. So one method that you could try is tracking everything by hand, manually diet tracking. And if you go online, you can search the USDA, United States Department of Agriculture food database, and just type that into your browser. And here I'm showing an example. If you type milk, there are over 6,000 different possible matches. So this is overwhelming, and some of these aren't even related to milk. So you can see there's candies and milk and cereal bar and protein supplements. So we want to be able to find something more meaningful as a match in the database. And you could try these existing applications like MyFitnessPal or Lose It are the common ones. And these are still a little bit tedious and time-consuming, where you have to type in one food item at a time and scroll through a long list of options to find the best match. So when I was first starting my PhD, as Jim mentioned, there were these nutritionists at Tufts University who approached us, and they said that their patients give up their weight loss goal after a few days because it's so hard to do this process of diet tracking. So they said maybe speech would be a more natural input modality, and people could just log what they're eating by naturally describing what they ate. So that was our goal. And our intent is to be able to have a user describe what they ate and map this directly to the USDA food database. So here the example is immediately it goes to chili with beans canned, rice white short grain cooked, and apples raw with skin as the best food database matches. And to do this, we used natural language processing, or NLP techniques, which is the intelligent understanding of human language, either written or spoken, by computers. And my focus is spoken dialogue systems. So I want to show you an example, a video of the Google Duplex system that was recently released and how natural this is to show you what's possible with NLP. So on the left is the automated agent that is booking an appointment for the client, and on the right is the real person at the hair salon. So just pay attention to the dialogue, how natural it sounds.
So how can I help you? Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second.
There's the natural pausing.
Sure, what time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like. What service is she looking for? Just a woman's haircut for now.
So notice that the Google Duplex system sounds natural in the speech that it generates and is able to understand the questions and respond back naturally as well. So when the person says this time is not available, it can reason about that and respond back with an alternate time suggestion. And what service is this? It knows how to respond back with just a women's haircut. And I want to show you an example flow through a dialogue system where we start with the user query, what the user says to the system. In this case, I drink a glass of Tropicana orange juice. And the first step is typically intent detection, where the system determines what the user's goal is, and here it's just logging a meal description. The second step is semantic tagging, where we go through the sentence and identify the key components and assign them semantic tags. So here, a glass is labeled as a quantity, Tropicana as a brand, and juice as the food. And then the final step is this database retrieval, where we take the semantic tagging information and then look up the relevant facts in a nutrition database in our case, and then respond back with that to the user. And maybe ask follow-up clarification questions, like was it with or without pulp, was it 1 cup or 2 cups, and so on. But in natural language, ambiguity is inherent. And there are much deeper ambiguities that are challenging in general NLP, but I'll show you some specific examples of ambiguity that are tricky in the nutrition domain. So what the person says might not match exactly what's in the database. An example of that is pluralization mismatch. Say the user had a strawberry, but it's actually strawberries in the database. Or there could be a tense mismatch, or capitalization and possessives is a common thing that we see in meal descriptions. And one pre-processing technique that's common in NLP is to tokenize the sentence first. So take in that meal description and then process it into words or subword units, which are known as tokens. And here, Kellogg's cereal gets parsed into Kellogg, the possessive, and cereal as the 3 tokens. So now these are the 4 different steps in this dialogue system framework, starting with the user query, which could be either spoken or typed. So if it's spoken, it goes through the speech recognizer and then gets transcribed into the text, followed by the language understanding component. So I worked on 2 tasks here, semantic tagging and database retrieval, and that gets followed by the dialogue manager, determining how to respond back to the user. And I also looked at these 2 tasks, 3 and 4. The follow-up clarification questions is if the system is unsure, it wants to ask a clarification question before responding back. And the 4th task, dialogue state tracking, is in my more recent work, which I won't have time to go into in this talk. But I applied the same types of models to this, where the goal is to track the user's semantic tags over the full course of the conversation, updating that as they provide new information or corrections. And I showed that with my models, we can avoid the pre-training and the handcrafted semantic dictionaries that are typically required for this. So each step, we run into that same issue of the language ambiguity and text mismatch. And typically, this requires a tremendous amount of manual text processing. So we want to get away from that. And for my thesis, I've been exploring deep learning techniques. So moving away from the handcrafted feature engineering and really seeing if we can feed the raw natural language into the neural network model to handle the text mismatch internally. So to give you guys some background, I know most of you are very familiar with deep learning already, but this is a type of machine learning. And in particular, we're looking at neural network models, which are inspired by the human neural network in the brain. And these are these circular nodes or neurons that are connected in a series of layers. So at the bottom, we have the input layer, which in NLP would be text, maybe a sentence, and then it's fed through a sequence of stacked hidden layers, which if there are more, then that's considered a deeper neural network, and that's where we get deep learning from. And the output layer, in this case, is a sentiment analysis task, predicting the correct label given that input sentence. And here, the sentiment or emotion would be happy. And deep learning is not a new technique, so this has been around for decades, but only recently has it become successful due to all the large quantities of data we have available, powerful computation methods, and the right training algorithms. So these have become state-of-the-art in computer vision, understanding images, speech recognition, and NLP. And I'm going to show you a couple examples of neural networks that I have explored in my work. A recurrent neural network has these recurrent connections at the hidden layer from the previous time step to the current time step. And that allows us to handle the order that we want to preserve in sequences of text and sounds and speech. And it can preserve the history, what we've already seen before in the past. And a convolutional neural network is popular for computer vision, where typically the input is an image, like you see in blue, and there's this gray convolutional filter that's slid across patches of the input image, and then outputs at the top that green output layer. Okay. And background on word representations, this is a very common way to handle text in neural networks. So we have at the first layer this word embedding layer, where we're essentially mapping a word into a vector of numbers representing that word. And the nice thing about word embeddings is that they represent this distributional hypothesis, where words that occur in similar context tend to have similar meaning. So to show you to give you some intuition, let's say in the training data we have a sentence, I ate a slice of toast with butter. Then we're learning this vector for toast based on the context it tends to appear in. Bread might tend to appear in similar context, and then you would learn a similar vector. And maybe if we learn a vector for crackers, it might be in slightly different context and have a different vector. So if we look at this in 2D space, we might see bread and toast lie close together, and crackers might be a little bit further away. And what's really important in machine learning is the training data that we collect and use in order to learn these models. So in my work, we have two different data sets. We have the structured food database, and we have natural language meal descriptions. So for the structured data, we can just use the USDA, freely available online, which has over 200,000 different food items and their nutrition facts, the calories, the protein, the carbohydrates, and the vitamins and other nutrients. And we also need some way to get meal descriptions and tags and labels for these meal descriptions. We need semantic tags, and we need the matching food database entries. So what's commonly used for this is crowdsourcing. So we can launch a task and pay a worker to complete the task for us. And in our case, we ask them to write meal descriptions, given matching food database entries. So we collected over 100,000 different meal descriptions on AMT. And this is what the interface looks like. So don't worry too much about the instructions, but essentially we would assign a meal category to the task. In this case, it's smoothies. And we would have randomly selected food database entries that fit into that meal category. So here there are fruits and vegetables and juices. And we instructed the worker to select at least 3 different food database entries and then to write a meal description about those. So that gives us the link between this meal description and the matching database entries. We also wanted to get semantic tagging data. So we would, again, ask Mechanical Turk workers, given this meal description, label these semantic tags. And we had a cup, as an example, labeled as a quantity in yellow, and 2% in that sentence labeled as a description in green, and milk labeled as red. So that's how we're getting the semantic tagging data. All right, so now I'm going to go into the first task, semantic tagging, where the setup is we're predicting BIO labels for each token in a meal description. And B, in this case, is the beginning of the semantic tag. I is inside the semantic tag, and O is other. So, for example, chocolate chip granola is a description of the food bar. So chocolate would be labeled as B description for the beginning of that. And chip and granola are labeled I description for the inside that tag. And I had is labeled O for other. And the first model that I explored here in my master's degree was the conditional random field model, which was state-of-the-art then. But this required handcrafted feature engineering like n-grams, the exact word or sequence of words, part of speech tags. So maybe a food is more likely to be a noun, and a brand or a description is more likely to be an adjective, and other features like word vectors, proto-site similarity, etc. So now we can use neural networks to avoid this feature engineering, and they learn their features automatically during training. So what does this model look like? We have the user's meal description coming in as the input, and that gets fed through a word embedding layer. And then the task-specific model is trained on top of the word embedding. So that could be a CNN or an RNN, and predicts these BIO labels for each token as the output. And I also looked into a more recent model called BERT, which if you're not familiar with word representations, don't worry about it, but this now is learning contextual word representations, where it takes in the entire sentence in order to generate a word embedding, and it's pre-trained on a very large separate data set. So now the emphasis is entirely on the word representations instead of that task-specific model. And after the word representations, we just have a simple single feed-forward token classification layer that's fine-tuned on this task. And to evaluate this, we had written and spoken meal descriptions that were held out as a test set. And my lab mate, Dr. Michael Price, and I collected a subset of these where we asked Turkers to read it aloud. And then we got the spoken version of the meal description. And Michael trained a speech recognizer and Caldi on this, got 8% word error rate, and then we were able to feed in the test set and get the spoken or the transcribed versions of those meal descriptions. And the metric here that I'm going to show is F1 score on the x-axis, where 100 is best, just like accuracy, and it's the harmonic mean of precision and recall. And the y-axis are the semantic tags, with the average over all of them at the top. So here in blue, I'm showing the conditional random field model results. In red are the convolutional neural network, which is slightly better. In gray is the RNN, and finally in yellow is BERT, which is slightly better than the rest. So in general, we see that these neural network models slightly outperform the CRF on this spoken test set. And one thing that's interesting is the performance on brands is a little bit lower than the other tags, and I looked into this and saw only 3.4% of the test tokens were labeled as a brand, and there's difficulty distinguishing between brands and descriptions. And that is also comes out with the speech recognition errors. So I looked at one example and saw Don Julio tortillas, which should be labeled as a brand, was misrecognized as on whole wheat tortillas. So now it might be labeled as a description instead. And in general, I tend to prefer the CNN architecture. I like the efficiency of it, the fewer parameters and training time, and the interpretability aspect. So now that this model is trained, I can go back to the filters and figure out what are they learning. So I went back and I fed in all the words in the vocabulary to determine which words had the highest activation energy. And I picked out a couple different filters where I saw patterns. So in filter 52, it seems to be identifying carbohydrates, like rice and potatoes. And the first filter seems to be picking out different types of protein, like fish and meat. And now I'm going to show you that my model is generalized to other domains beyond nutrition, like restaurant booking and flight booking. So for the restaurant domain, this was data collected, again, by a previous lab mate, Dr. Jingjing Liu. And she went to Amazon Mechanical Turk to collect these queries about restaurants. So now it's still BIO labeling, but the tags are different. They're related to restaurants like cuisine, location, price range. And again, she used a conditional random field model with carefully handcrafted features And those are related to parse trees. So don't worry about parsing if you're not familiar with it, but it's an important concept in linguistics and NLP, and it represents the syntactic structure of the sentence. So she picked out syntactic and semantic dependency parse features for her CRF. And I'm showing here, again, the F1 score on the x-axis for this task, and on the y-axis are the different models. So the neural network models seem to be performing better than the CRF, and BERT is the best. And finally, I looked at Air Travel Information System. ATIS is this popular flight booking dialogue data set from the 90s. And here, there are over 100 different flight-related semantic tags, like departure city, or airline, or arrival time. And again, we see similar performance, where at the top are the neural models that seem to outperform the CRF and other statistical models at the bottom. So that concludes the second part of my talk on semantic tagging, where I've shown that the CRF, which requires handcrafted feature engineering, is outperformed by these neural network models that learn their features automatically during training. So now moving on to the second part on database retrieval. The first attempt was what you might imagine doing, where we first took a user description, we performed semantic tagging, and we identified and extracted these food concepts based on those semantic tags, and did a string-based exact word match lookup in the database. So I worked with Master of Engineering student Rachel Naftal on this, and we had this complicated pipeline where first we would check, is there a brand match in the database? Among those, is there an exact food match? If not, then we have a backoff mechanism, check singular first, then check plurals, and vice versa. So this works well if you have an exact word match in the database, like orange juice. But what happens if there is a mismatch, or it's not quite worded the same way in the database? So if the user said they had toast, in the USDA food database, we have various types of bread that are toasted, and we have toasted nuts and toasted cereal and French toast. So how do we handle this ambiguity? Again, we use a neural network model that can learn semantic vector representations of the language in order to handle this mismatch. So this is an illustration of what I mean. The user query comes in, say, I had a slice of toast, and that's fed through the model. Then that generates a vector representing that user query. And in vector space, it should lie close to semantically similar database entries. So any food that is similar in meaning should lie close to that vector. So that would be the bread, different types of bread cluster, and then crackers should be its own separate cluster, and French toast as well. And I'm now going to show you a TSNE plot of these vectors that we actually learned with our model. And this is just for visualization to see, is it learning what we'd expect? So here each point is a food database entry, and its location is based on that learned embedding, and the color is the food category. So what you would expect is that foods that are from the same food category are probably similar in meaning and should cluster together. So we see that with this cluster. We see that breakfast cereals in yellow tend to cluster together. The dairy and egg in red have clusters, so you might imagine one is eggs, one could be yogurt, one might be milk, and baked products cluster together in green. So how did we train this model? We had two different inputs that we fed to this model: the USDA food database match and the user's written meal description. And we asked the model, are these a match, yes or no? So the USDA food database and the meal description get fed through a shared word embedding layer. Then there's max pooling over one of them and a single convolutional layer over the meal description with filters that span windows of 3 tokens. And we perform the dot product between each token in the meal description and the USDA food item, where you can use any similarity metric, but that worked best for us. And that was followed by mean pooling, and finally at the end, just a binary sigmoid output layer saying, is it a match which would predict a 1, yes, or no, which would predict 0. And it's important to note that this model is trained with weekly annotated data, so we did not tell the model where in the meal description those matches occurred. We, if you remember the AMT data collection, asked workers to write meal descriptions about 3 or more foods. And we don't do any pre-processing. We don't do semantic tagging to tell the model any information. All we do is tokenization as pre-processing. And the model has to figure out where the matches occur in the meal description. So at test time, what does this look like? The user meal description comes into this neural network to generate this learned semantic representation. And in the database, we have pre-trained word embeddings as well for each of the food database entries. So now we can just rank them based on the similarity score of their learned embeddings. And then the ones that are most similar in meaning should rank at the top. So now to show you that this model is doing what we would expect, I took a test meal description that the model has never seen during training, and I found the top matching food database entries and where exactly they map to this sentence. So the x-axis are the tokens in that meal description, and the y-axis is the similarity score. So I fed it through that convolutional layer, and then these are the dot products that come back. So each colored line is a different matching food database entry. And in blue, the top match is McDonald's Big Mac, which makes sense because it overlaps in terms of wording with a Big Mac. So that's where it has the highest similarity to this sentence. And more interesting, there's cheeseburger, which also maps to, which has a high similarity score with a Big Mac, even though those are different in wording. So the model learns that those are similar. And catsup is the name of ketchup in the database, and it learns that it's the same thing as ketchup. And a peeled banana as well, even though there's the difference in pluralization, wording, and capitalization. So that confirms that the model is doing what we'd hope. And more analysis, you can take a database entry and find its nearest neighbors in the database based on that learned embedding and the similarity score to all the other database foods learned embedding. So here I looked at the nearest neighbors for this fried chicken breast and saw that they were fried chicken drumsticks and KFC fried chicken. So that, again, confirms our intuition. So that concludes the second part of my talk on database retrieval, where we have shown that there's this ambiguity in mapping from a raw user natural language query to the structured database matches. And we can use a neural network model to learn these semantic vector representations in order to do this retrieval. And now I'm going to move into the third and final part of my talk on asking follow-up clarification questions. So why would we want to do this? We already have that ranking, but since there are so many database options, there are over 200,000 foods, it's hard for the model to be able to directly predict the exact right match. And people are not always precise when they describe what they've eaten. So ideally, we could ask follow-up clarification questions to narrow down the database search space. And on the left, this is an illustration of what this might look like. Say the user had a bowl of oatmeal, and then the agent asks what was the brand, and the user says it was Quaker. Now we can immediately narrow down the database entries to only Quaker oatmeal options. And the challenge here is we want to avoid asking too many questions, so we don't want to overwhelm the user, and we want the questions to be intuitive. So we want to make sure if they log vegetables, for example, we don't want to ask about caffeine level. And here we can use reinforcement learning to design a reward function that balances these two things. We want accuracy in terms of food prediction, and we also want ease of use, not asking too many questions of the user. And this is showing you how this fits into the overall pipeline with the previous two steps that I talked about, semantic tagging and database retrieval. So it still goes through the tagger first, and then we take a tagged food segment and do the database retrieval. And asking follow-up questions is part of that database retrieval process. So the first ranking comes from the learned embeddings similarity scores that I described in the second part. And now in this part, I'm describing how we narrow down and re-rank those initial rankings by asking the user follow-up clarification questions. And then once we've narrowed it down to the top 5, we can return those to the user. So before I get to the reinforcement learning, I want to go over 2 different baselines that we explored. First, the rule-based ask questions in this predefined order, where there are 12 different possible questions related to food attributes. So they might be something like the category of the food. Was it a cereal? Was it a fruit? What was the brand? It could be Quaker or something else. What was the milk fat, the sweetness amount, the salt amount, etc. And the second baseline is entropy. So asking at each turn the question that maximizes the information gain and reduces entropy. So to illustrate this, give you some intuition, let's say we have 3 different yogurt options that we're trying to narrow down to 1. If we were deciding between these 2 questions, asking about the category and asking about the milk fat, then if we ask about the category, they're all dairy. So now we don't get any new information from that. But if we ask about milk fat, then they're all different and we can immediately narrow it down to just one option. And for reinforcement learning, the typical framework is you have this environment that you transform into some state that can be fed through something known as the Q network that predicts a Q value for each possible action that can be taken. In our case, the action is the food attribute. And the Q value is the expected sum of future rewards if you were to take that action. And then we take that action that has the highest Q value, update the environment and the state, and continue the loop until the dialogue is completed. So the action is which food attribute do we want to ask about? And that could be category, brand. And the question that actually gets asked is just a simple template where we plug in the attribute that was selected as the action, and we plug in whatever the tagged food item was that the user logged. So it might be if we select brand as the action and the user was talking about oatmeal, then the question might be what was the brand of the oatmeal? And so that was the upper right corner of this illustration, and the state in the circle at the bottom is the tagged food segment and the one hot vector of the remaining top n ranked foods. So that's a vector of zeros except for 1 for each of the foods that is still in the ranked list, and a binary action mask. So we want to mask out anything that doesn't yield any new information or that has already been asked before. And the reward function is don't worry about the equation, I'll just explain the intuition, but it's used to update the Q network, that box in the middle, its parameters during training. And the intuition is that the first line is a slight negative reward or a slight punishment if it continues the dialogue without ending it, because we want to keep the dialogues as short as possible. The middle line is a positive reward, positively reinforcing the behavior if we end the dialogue, and the correct matching food is ranked in the top 5. So that's good behavior that led to that outcome. And if we get to the end of the dialogue and the best match isn't in the top 5, then we punish it with a -1. And the Q network is designed with the tag food segment coming into the word embedding layer and then max pooled and concatenated with the top n ranked foods. That's fed through a feed forward layer and is masked with the binary action mask. So then we get the probabilities for each action and we can select the maximum. So at test time, what does this look like? We have the user query coming in, which might be a slice of bacon, and then the system has to determine which food attribute to ask about. What's the action? It might decide preparation style. So then the question is, what was the preparation style of the bacon? And it provides options for each of those in the top n ranked list: pan-fried, baked, or raw, which I hope it wasn't raw. And then the user will determine the right answer, and that's how the system will respond back with the top 5. If it's pan-fried, then it will return these 2 database entries. So to evaluate this, I use 2 different methods. I use a user simulator, which we assume always answers the questions correctly, and evaluate it on humans. And the metric here is recall score. So top 5 recall is how often the correct food is ranked in the top 5, and top 1 recall is how often it's the exact right match. And here I'm showing you the baseline, which is what the output of part 2 of my talk, without asking any follow-up clarification questions. If we just use that initial ranking from the learned embeddings, similarity scores, what performance do we get? And as soon as we add in follow-up clarification questions with entropy, that boosts the top 5 recall score from 55% to almost 90%. And the rule-based approach is also higher than no follow-up, but slightly lower in terms of recall score. And finally, the reinforcement learning agent is somewhere in the middle. It's also high in terms of recall, but if you notice the asterisks indicate statistical significance with respect to reinforcement learning, entropy is actually not significantly better than reinforcement learning. But in general, asking follow-ups does help improve the recall. And the other interesting piece of this is the ease of use. So we can look at how many questions were required on average in order to end the dialogue. And here, a lower value is better because we want shorter dialogues. So entropy, even though it had the highest recall, has the longest dialogues with 6 on average questions. And rule-based is the shortest. And reinforcement learning, again, is in the middle, but still relatively short at around 4 questions per dialogue. So we see that there's this trade-off between food recall score and ease of use in terms of the number of questions required. And the reinforcement learning agent seems to be able to strike a balance between those two. And as I mentioned with the user simulator, we assume it always answers the questions correctly. So we also evaluated this with humans on Amazon Mechanical Turk to make sure that we see if it works in the real world too. And we can ask them to interact with the system to get the recall score as well as evaluate the system afterward, say what their perceived rating is of the accuracy and the naturalness of the agents. So the interface here provides the worker with the meal description and the matching food database entry. And then at each turn in the dialogue, the system suggests a question, a follow-up question with a food attribute and the possible options with numbers. Then the user types in the number for the attribute that they think is the right match. They press the button to continue the dialogue, and then it continues until they're down to just 5 database matches. So here we see the same pattern in the results, where entropy has the highest recall and the longest dialogues, again, and the rule base is on the other end of the spectrum with reinforcement learning somewhere in the middle. But what's pretty interesting is the perceived accuracy and naturalness of these systems. So in terms of accuracy, which you can think of as similar to recall score, entropy has the highest recall. But if you look at the perceived accuracy in green of entropy, it shows that it's actually, so entropy is in the middle here. It's significantly worse than reinforcement learning. And if you look at yellow for naturalness and ease of use, blue at the top for reinforcement learning, it's significantly better than the other 2 models. So I wanted to dig into this and see, is there some reason that reinforcement learning seems to be perceived as better? And I found that the types of questions tend to be more intuitive. So on the right-hand side are the foods that are the correct match that were described by the user. On the left-hand side is the question, the follow-up question that the reinforcement learning agent asks. And this set appears to be intuitive, where if the food contains a brand, then the RL agent asks, what was the brand? If it is cookies or meat or cheese, then it asks, what was the fat content? And for drinks and fruit and canned vegetables, it asks about packing style. And for vegetables and cheese, it asks about salt. So for me, that seems like they're fairly intuitive questions. So that concludes the third part, where we were looking into asking follow-up clarification questions to narrow down the database search space. And we saw that with reinforcement learning, we can balance this trade-off between accuracy and ease of use, and it's rated the most natural agent. So now I'm going to tell you how we built our system and how we evaluated it. So we took the semantic tagging and database retrieval, and we deployed a real-world system, and we evaluated it in 3 different ways. So first we went to Amazon Mechanical Turk, and we asked workers to log 3 different spoken food descriptions and to interact with the system. So we would predict the top 15 foods and ask them to select the correct one or none if they're all wrong. We asked them to also select the correct quantity for the matching food. And in that way, we got more data as well. So we can evaluate it and we can continue collecting real-world data. So we have over 150,000 spoken food logs from Amazon Mechanical Turk and those matching food and quantity results. And this plot is showing you how the system performance improves over time. So the x-axis is each batch of 1,000 tasks that I launched to Amazon Mechanical Turk in order. And the y-axis is recall score. So each line is something like top 5 food recall, top 1 food recall, quantity recall. And the main takeaway is that over time, it seems that this system is actually learning from interacting with the users and improving. So that's encouraging. And the second way we evaluated this was with our Tufts nutritionists. So we did a study already with 14 participants, and now we're doing another one with 30 participants. This is our ongoing work. And we asked them to use the system to log their food for 5 consecutive days, and the nutritionists would do 2 24-hour dietary recalls. where they would ask the person exactly what they ate, and we could use that as our ground truth, what the correct number of calories were per day. And then we can compare that to our system. So we found that there was a significant correlation between our system and that of the nutritionists. And the Pearson's correlation coefficient is 0.58, indicating positive correlation, and the p-value is less than 0.05, which indicates that it's significant. And finally, we have built, with a team of undergrads, an iOS application, which we deployed to the Apple Store in January. So this allows us to actually collect real-world data with people who care about tracking their diet, get feedback from them, and more training data for our models. So this is Cocoa Nutritionist. If you're interested, feel free to try it out. And now I'm going to do a quick demo. So this is the interface with the chat screen, and I can either log my meal with speech or in the text box with typing, so I'll just use the microphone here. For breakfast, I had an apple with 2 tablespoons of peanut butter. And you'll notice the first step is the semantic tagging, where it identifies apple as a food, peanut butter as a food, and 2 tablespoons and an as quantities. And then it does the database retrieval step, where you can now select a different food option from the top N or a different quantity. So I might select 1 medium apple, and maybe I actually had chunky peanut butter, so I can change it to the second top ranking. And you can also look at your timeline, history of meals that you've logged, and trends, a breakdown of the different nutrition facts. We have a lot. And I apparently eat a very high-fat diet, shown in purple. Okay, so that is cocoa. And now, since we had this in the Apple Store for 2 months, we have some statistics on its usage patterns. So here is a histogram of the users and the number of days that they've logged with cocoa. In the x-axis, you see this really long tail. So the y-axis is the number of users who have logged this many days, and 293 only logged for 1 day. So that's kind of expected, I think, because it is a difficult process of diet tracking. But what's encouraging is how many users there are on that long tail who actually kept up with it for 10 plus days or 20 or more, and 1 user for 30 and 1 for 40. And the 40 days wasn't me. And there's distributions of number of words per log, which is interesting. Spoken in blue and written in red. So if you look at the x-axis, that's the number of words per log, and the y-axis is the frequency, the number of people who logged that much, or the percent. And the written logs actually have a peak at only 2 words per log, whereas in speech, there's this longer tail, which indicates to me, at least, that people tend to have more wordy descriptions and more natural descriptive meals when they're logging with speech. So that motivates our use of this voice interface. And in addition, there was fewer capitalization and punctuation in the speech. So the recognizer doesn't, we're using Siri recognizer, it doesn't always predict punctuation, and people might be more formal when they're writing. Oh, and now I'm going to show you play some sample recordings so you get a sense of how this is real-world data. With background noise.
Tuna and cake and chocolate-covered pretzel.
And we have 58 users from the UK. We
Omelette
have different accents.
with 2 eggs, half a cup tomatoes, 1/3 cup onions.
And we have babies.
Half of a cheese quesadilla.
That's a rocket. That's a rocket.
And you can go,
Explaining how to use cocoa.
ham sandwich, please. Oh, that's it.
Which sometimes gets misrecognized, so Siri is not always correct. It was recognized as, you can go camping with us, please. So right now we're thinking about building our own speech recognizer that might be able to be nutrition specific and use that language model instead. So more future work. I want to make Cocoa more interactive. So right now the user can log what they're eating, and then it'll respond back with the nutrition facts. But some people want to be able to ask questions and have more of a chat feel with Cocoa. So maybe they could ask something like, which has more spinach, or which has more iron, spinach or kale. And then Coco could respond. And some users have asked for personalized food recommendations. So they really want to know what's a healthy snack that they can eat next that fits into their daily calorie goal. Maybe it's based on their history of foods that they tend to like to eat, and could also be high in nutrients that they're missing for that day. And a lot of people have said, I just want to take a picture of my meal. And there are apps that do that, but maybe we can combine these two modalities of computer vision and speech and language. So let's say someone takes a photo of their glass of milk. Maybe a computer vision algorithm can identify that it's a glass of milk, but not necessarily know what type percent or what percent milk fat it is. And that's where the dialogue can come in, asking a follow-up clarification question about the milk fat to disambiguate that. And now for my acknowledgements, I want to thank my advisor, Jim Glass, who has been training me as a researcher and supporting me in my PhD for the past 6 years. So thank you, Jim. And to my committee, Pete and Victor, and for all of your helpful advice in reading my thesis and guiding me in the last couple of years, and especially Victor for accepting me into MIT and convincing me to come here, because I really enjoyed it. I think I made absolutely the right decision. And still being on my committee and writing me recommendation letters, even after half retired. And for Spoken Language Systems Group, SLS, you guys have been the best lab mates that you could ever ask for. I've included graduates and current postdoc office mates, Hao and Francois. Thank you guys for always supporting me every day, being in the office with me, and I only wish I could be half as brilliant as all of you. You guys are awesome. And Marcia, I cannot forget Marcia, our administrative assistant, who has been there every day helping me with my work and personal advice, life advice. So thank you, Marcia. And my best friends at MIT, Danielle and Jennifer and Amy, Ramya and Mengfei, who may be watching this in Singapore, my roommate of 5 years. Thank you guys for being the best friends and support group anyone could ever have. So we have girls' night all the time. We're going to have one tonight, and we have lunch every week. So I'm going to miss you guys when I move back to California. And my East Coast relatives, who basically took me under their wing when I moved across the country 10 years ago and drove me back and forth to Danvers for numerous family get-togethers. So I'm really grateful to them, and most importantly, to my parents and my sister. So I want to thank them for their love and support throughout my whole life, and especially during grad school and in preparing for my future career as a professor. I couldn't have done it without them, and they're always there for me, no matter what. And to my sister, who I want to wish luck on her PhD at the University of Florida in organic chemistry, following my footsteps. And then for the next stage of my career, I'm excited to go to Loyola Marymount University as an assistant professor of computer science there. So I'm excited for that in LA. And finally, to conclude, I want to go over the contributions of my thesis. In general, I have shown that this deep learning technology can be applied to other tasks outside of the ones that I've shown, like dialogue state tracking and other domains beyond nutrition, so restaurant or flight booking as an example. And I have demonstrated that this weakly supervised convolutional neural network can learn semantic vector representations of the language in order to map directly from a raw natural language user query to a structured database match. And we can use deep reinforcement learning in order to ask follow-up clarification questions. And finally, I have built this with a team of undergrads diet tracking application for iOS. So with my deep learning technology for spoken dialogue systems, hopefully people will be able to track their dietary intake more easily and efficiently. Thank you.
So you didn't talk about the intent recognition part
Oh, right.
of the system, but what happens if I do something that you're not expecting? Like I talk to the system and I say, I threw out my glass of Tropicana orange juice because it had turned green, right?
Yeah, we can test it right now, but since we don't have the intent detection piece yet, it will identify the Tropicana orange juice and assume that you ate it. So that's future work, being able to know even other subtleties, like if they said know without this being able to recognize that that food was something that they didn't have instead of something that they ate.
And if you look at the Amazon Turk or the app interactions, do you find oddball things like that? Or do you
I've actually,
much stick to the script?
I have found some users trying to say things that I wish we could do, but that we don't. So then it makes me realize that we need to add that feature now. So for example, someone was saying, oh, yesterday I had the same thing, or today I just had the same thing that I ate yesterday for breakfast. And I thought, oh, that's true. If you're talking to an artificial intelligence agent, you might expect it would be able to understand that, but it doesn't. And people have said the thing that I already mentioned, like, oh, I had this chicken thigh without the skin. And so it doesn't necessarily pick up the without piece. Yeah, good question.
Surely somebody has a question.
Victor.
This is a quick question. I found what you described and the things that you built to be very U.S.-centric.
Mm.
And I cook 90% of my meal in Chinese.
Yes.
And I can't just say I had Kung Pao chicken for dinner. Like, how easy is it for you to generalize beyond the United States?
Yeah, that's a good question. Unfortunately, we're limited right now to the USDA food database, which is mostly American food. But there are people, like my parents' friends, who have said, oh, I mostly eat Chinese food, so I'm not a good user for you. And then I think, okay, we need to transfer it to other domains and people who are using it in China. I think we have around 20 plus users in China. And we probably just need to be able to find that database of food, and then hopefully the learned embeddings will already map to those. But if they're unknown words, then I think we still need to collect new data. If it's something like Kung Pao chicken, I guess if it hasn't seen that already in the USDA, then we would need more training data.
It's a good question, though.
Yeah.
Like, you just use the USDA, but certainly other places around the world
Yes.
have similar kinds of.
And one of the computer vision apps that I saw was Japanese food only. So I think they have at least lots of pictures of Japanese food, and then they probably have descriptions. So that's one idea.
One of the things that's changed over the course of your thesis is that more data has become available.
Yeah.
When you started, it was just the standard reference.
Yes. We started with 8,000, and then they added all the branded foods 200,000 later, and we had to add that in.
And restaurant food.
And now we're looking into restaurants. So some undergrads have been working on scraping restaurant websites for nutrition facts. Yeah. Stephanie.
You haven't made it clear exactly how much processing is done on the food that you talk about, and then bring it back into minerals, vitamins, fats, in other words, kind of food composition. I guess that part's there, because I saw something.
Yeah, that comes from the database. So we're just doing the mapping to the food name match, and then the database already has all those nutrition facts and serving sizes. So one thing I didn't talk about was quantity mapping, and I do have some work on a multitask learning neural network that can predict the food and the quantity at the same time.
But do you get quantity usually, and then you actually compute the total amount of different minerals and vitamins and whatnot, then when you couldn't imagine that you're actually, like you say, advising the person who should eat more vitamin C, try to eat some more vitamin C.
Yeah, we do have information about exactly how much we think they've eaten of every nutrient. And right now, it just says the next day, if you're low in some nutrient, it says, oh, you ate this much out of what we think you should be eating for this vitamin. But
Yeah, I saw that.
yeah,
Yes.
yes.
That's an excellent
Yeah.
application for it.
How is the work related to the speech recognition? And how accurate, what's the accuracy rate?
Oh, actually, that's something that I wanted to measure, because we have two different recognizers that we're using, the Siri recognizer in the app and then Google in the browser when we do AMT. So I wanted to build our own recognizer, and then on that data set that Michael and I collected, then be able to evaluate those performances. So I don't have those numbers yet. But yeah, it would be interesting.
Another fun idea might be if there's somebody who's trying to enter a food that's not in a database or they can't find it, to be able to take a picture of the nutrition facts on the package and use optical character recognition to get all of the nutrients in the serving size.
Yes. that is definitely one idea we've discussed, because I think some of these apps like MyFitnessPal actually allow people to type in the nutrition facts if they can't find it in the database. But we didn't want to let them have that much freedom in case they type something wrong. But yeah, if you do it automated with the optical character recognition, I think that would be a good solution. Yeah, Jen.
Two thoughts. One is MyFitnessPal also has a barcode scanner that
Oh, yeah.
goes right to the database, which is nice. You don't have to
We added the barcode scanner when we got feedback about that. But sometimes it's not in the database. The barcode is missing. Yeah.
I had probably a very narrow question, but I was wondering about the reinforcement learning, how much you played with the reward function and whether you found that the results were like really dependent on the specific values that you chose, or whether there was some.
For me, it seemed like even when I played around with it, it tended to have like the exact same performance. So there wasn't much variability in that. Yeah. Thank you, guys.